In this video, I'm going to be reviewing circular motion and centripetal forces. Remember that when an object is traveling in a circular path, there must be something that's forcing it to travel in a circular path, because Newton's first law, the law of inertia, says that an object wants to travel in a straight line, or if it's at rest, it wants to stay at rest. In this particular case, we have an object, a mass. It could be a ball, it could be a weight. It's attached to a string. The red rectangle is the mass, and the blue line is the string. So this object is constantly being rotated in a vertical circle. And let's say it's being rotated in a counterclockwise direction. So this object is constantly rotated in a vertical circle. Now keep in mind that the object doesn't want to travel in a circular path. It wants to travel in a straight line. So if this object was traveling in a counterclockwise direction, at this point, if the string were to break, the object would go straight up because the velocity is pointing always tangent to the circular path. So the object would go straight up. But if the string broke at point A, then the object would go to the left. If the string broke at point B, the object would shoot out towards the right. But if the string stays unbroken, if it keeps the object traveling in a circular motion, then the velocity vector is constantly changing. So the velocity is changing because its direction is changing. Now its magnitude may not change. As this object travels around in a circle, it may maintain a constant speed, a speed of 5 meters per second, or 6 meters per second, or a speed of 2 revolutions per second. Even if its magnitude doesn't change, but its direction is constantly changing, then the velocity vector is changing. Because velocity, keep in mind, is a vector, and it requires two things. It requires a magnitude and a direction. So even if the magnitude isn't changing, but the direction is changing, then the velocity vector is changing. And if the velocity is changing, then there must be an acceleration that's causing that change. And if there's an acceleration that's causing a change in an object that has mass, then there must be a force that's causing that change also. In this particular case, the velocity is constantly changing because the string keeps pulling the object back in. The object wants to go in a straight line. The object at this point wants to go straight up. The object at point A wants to go to the left. The object at point B wants to go to the right. But the string keeps pulling it back in. So the string is exerting the force needed to keep the object in the circular path. So the string is actually exerting the centripetal force in this case. Now, whenever we have a force in a string or a rope, we call it a tension force. And I've labeled it here with a capital T. And you can see it in the drawing too. It's labeled as a capital T. The tension force is the centripetal force in this particular scenario because the tension force is pulling the object back in towards the center. The object doesn't want to travel in a circular path. It wants to travel in a straight line. In different examples, the centripetal force varies. So for example, if you talk about the moon and the earth, and the moon is orbiting the earth, well, the moon doesn't want to travel in a circular path. It wants to travel in a straight line. But the force of gravity between the earth and the moon keeps pulling the moon back in towards the earth. So it forces the moon to rotate around the earth, maintaining a circular orbit. And in that particular example, the force of gravity is acting as a centripetal force, because any force that points towards the center can be labeled as a centripetal force. Keep in mind, centripetal force isn't a new force. It's just a naming convention for a force that points towards the center. If you have a car going around a racetrack, and if it's a circular racetrack, well, in that case, the force of friction is what keeps the car on the racetrack. Because if there wasn't any friction, the car wouldn't stay on the circular racetrack and would go tangent to that circular path, and it would end up hitting the wall that surrounds the racetrack. So if you have a car traveling in a circular path on a racetrack, then in that particular case, the force of friction is what's constantly changing the direction of the car's velocity. And thus the force of friction is responsible for the centripetal force that keeps changing the direction of the car. In this case, we have the rope. So we have a rope spinning a mass in a vertical circle. So the tension force is what's responsible for the centripetal force. I've drawn a couple of force vectors for you over here. At this point, the force of gravity is pushing the box down. The tension force is pulling towards the center. At point A, the force of gravity and the tension force both are pulling you towards the center. At point B, the tension force is pulling you up. The force of gravity is fighting against you. It's pulling you down. The force of gravity will always point you towards the center of the earth. The tension force is always going to point towards the center. So at point A, the centripetal force at point A is found by doing the force of gravity plus tension force. At point B, the centripetal force is the tension force minus the force of gravity, because these forces are in opposite directions. In this case, they're in the same direction, so they've been added together. In this case, at point B, they're in opposite directions, so you can subtract them. Well, this is useful because many times they ask you to find the tension force, and you notice to find the tension force at point B, if you were to solve for T, the tension force, you'd have to take the force of gravity over to the other side, and it would become T equals centripetal force plus mg. So the tension force is actually larger at this point than at this point, because at point A, if you solve for the tension force and you take the force of gravity over to the left side of the equation, it would become centripetal force minus mg is equals to T. So at point A, the tension force is less, and that makes sense, because at point A, the string has to do less work, because the force of gravity is helping you stay in the circle. This force of gravity at point A is pointing towards the center, so the tension force in the string has to do less work. You have to have less force in the string to generate the remaining centripetal force. In this case, the string has to do more work because it has to pull against the force of gravity. These two can be useful in calculating the tension force. You can also find out what the minimum velocity is required where there's no tension in the string, where the string is completely slack and the object still makes it up to point A and then comes back down. And if anybody asks you that question, to find the minimum velocity required, then you've got to remember, if the rope is completely slack at point A, then the tension force is 0. So then instead of saying the centripetal force is force of gravity plus tension force, you would say directly that the centripetal force is equals to the force of gravity. And then you'd use that as your starting point to solve for the minimum velocity that the object can have and make it over point A and then come back down and keeping the rope slack. The centripetal force equations are given to you up on the board. Centripetal force, just like any other force, is mass times acceleration. In this case, it's the centripetal acceleration. And once again, the centripetal acceleration is also pointing towards the center, but it's constantly changing the velocity's direction. The velocity, remember, wants to go tangent to the circular path, and the acceleration, centripetal acceleration and the centripetal force are constantly pulling the object back in to the circular path, so it maintains that circular path. The centripetal acceleration is calculated by doing v squared over r, the velocity squared over r. Remember, the velocity can be calculated by saying the circumference divided by the time to make one complete circle. The time to make one complete circle is called period. Be careful, this is a capital T and here's a capital T. Over here, the capital T is referring to the tension force. Over here, the capital T is referring to the period. So to calculate the velocity of an object traveling in a circular path, you can do 2 pi r over capital T, period. This is your period. This is your circumference. So that's your distance for one circle. This is the time for one circle. That can give you the velocity in meters per second. You can also calculate it in revolutions per second. Your centripetal acceleration is v squared over r, and your centripetal force, if you substitute your centripetal acceleration into your F equals ma equation, your centripetal force can also be written as Fc equals mv squared over r. If you needed to find out the minimum velocity needed for the object to go up to point A and come back down while the rope is completely slack, then at that point you would say the force of gravity is my centripetal force and the tension force is 0. Then you'd set the force of gravity, you'd set it equal to centripetal force, which is mv squared over r. You notice that the m's would cancel out and you would be able to solve for v.